Okay, so today we will start our chapter 2, electrostatic potential and capacitance. Today we will discuss the definition of electric potential. Then we will derive the expression of electric potential due to a point charge. And then we will derive it for due to a electric dipole placed in any region. Okay. Now, this electrostatic potential. Okay, so this is one of the most important physical quantity in electrostatic because it actually helps us to understand. It gives us clear picture that how electrons, when that suppose electrons in any wire. Suppose if you consider any wire and if you connect it to a battery, how the electrons present in that wire moves from one point to another, right, through that wire. So okay, so basically to understand that part we need to have a very clear idea about electrostatic potential. Okay, now before going into detail of electrostatic potential, we will go through a simple activity. Let's say that you are having these two containers, okay, and both of them are connected with this single pipe. All right. Now, since these two containers are at same height and both of them are connected using a single pipe, and they are having equal amount of liquid in both the containers. Okay. Since they are at same height, so there is no further flow of liquid through this pipe. Yes. So on one container to another through this pipe, there cannot be any more further flow of liquid. Yes. But still then if we want liquid to flow from one container to another through this pipe, we want that. So this can only be done if you give certain height to any container. Yes, if you see this figure 2, now this second container is given a certain height because of which the liquid starts to flow through this pipe from this container to this container. Yes, so this difference in height has actually made an impact which helped the liquid to flow from one container to the other container. Yes. Now how this is so? Why liquid is not flowing in this figure, and how liquid is flowing from this figure, from this container to this container. Now to understand this, let's recall the concepts of energy, okay, which we studied in earlier classes. Now we have studied in earlier classes that energy, it is of two types, kinetic and potential, right? Now if we define what is kinetic, so it is nothing but the energy stored in a body when when the particular body is in motion. Yes. And if we define potential energy, so it is nothing but energy stored in a body when that body is at a certain position. Yes, so this is how we define potential energy. Now if you see figure 1, these two containers, so they are at same height. Yes, from the base. So since they are at same height, so the potential energy for this container and the potential energy for this container, for both of them it is same. Yes, since they are having same potential energy, so there is no flow of liquid from this container to this container. Correct? But if you see figure 2, this container is given a certain height here. Right? Now since the height, he has been taken to a particular height, so the potential energy for this container has been increased. Because of this increasing potential of this container, liquid present in the air starts to flow through this pipe from higher potential to lower potential. Yes. Now this potential difference between this container and this container, this potential difference has helped the liquid present here to flow from this region to this region. Yes. Similarly, when we connect a wire to a battery, so the electrons present in the wire, they also experience certain potential differences due to the battery connected to them. Now that potential difference helps the electron move from one point to the other, through that wire. Clear? So we have understood that how electrons flow in a wire, due to potential difference. Now let us first define what is potential difference. But in order to define what is potential difference, let us first understand what is electric potential. How we can find the value of electric potential at a particular point. After defining the electric potential at a particular point, then we will define what is the potential difference. Okay. So in order to define electric potential, let us understand this slide. Here you are having this plus Q charge, positive source charge. Okay, so this is my source charge. This is my source charge. And he is generating an electric field of this much amount, kq by r square, right? And as you can see here, this boundary is actually the region where the strength of the electric field due to this charge can be felt. So within this region, you can moderately feel the strength of the electric field, beyond which the strength is of weaker, the strength is comparatively weak, okay, due to this charge plus Q. All right. Now let us consider another test charge. Now this is my test charge. Okay. So this is my test charge, Q naught, who is at very far distance away from this source charge. Okay. Now this test charge, who is at very far distance, let us assume that he is at infinity. Now we want to bring him from infinity to a particular point A, as you can see here. Now this point A is a point which is within this electric field due to this source charge. Now while this test charge, when he is coming from infinity to this point A, he does some work there, right, during his travel. So that work done in moving from infinity to this point A within the electric field. So that work done is stored at this point A, right? Now we want to know what is the electric potential at this point. So this is the expression of the electric potential at this point. So what we do here, so the test charge, okay, when he is doing certain work in moving from infinity to point A, that work we divide it by the charge value of this test charge. Since electric potential is nothing but the work done due to a unit positive charge, that's why we divide the charge value of this, the value of this test charge. So once we divide this work done with the value of the charge, we can actually find out the potential at that particular point. Okay. So if your test charge, if he's moving in this direction, and if he reaches here, okay, so work done in moving from this point to this point, so that work done divided by the charge of this test, the value of this test charge will give you the potential at this particular point, right? So in this way we find out potential at any point. Okay. Now we will find out potential due to a point charge. Now to understand this, let us concentrate in this diagram. Here also we are having this charge plus Q. Now this is my source charge, and he is generating a radially outward electric field, as you can see here. So this is my radially outward electric field Hence, this is my electrostatic force. Now, let's say that you are having a certain test charge Q0. Now, this test charge is coming from infinity in this direction, as you can see here, and he reaches point P, capital P, which is at r distance from this source charge. So in this way, we will be able to find potential at this particular point at distance r from this source charge plus Q. So when this test charge, when he's coming from infinity in this direction, which is against this electrostatic field, right? Electric field due to source charge. So when he's coming from infinity against this electric field in this direction, he reaches a point A, let's say, right? Let us consider that, he is reaching a certain point A, which is like x distance from my source charge. Yes. So when he is at point A, so he will be experiencing a certain force there, right? Which is nothing but Coulomb's force, as we know that. So which is 1 by 4 pi epsilon naught q naught by x squared. So this is the amount of Coulomb force experienced at this point, due to this source charge plus q. Now again, he's not going to wait here. He's going to move in this direction. So while moving in this direction, again he reaches another point. Let's say point B. And while moving from A to B, he's covering a distance dx, right? So since he is moving in this direction, so the work done in moving from point A to point B through a distance dx, now that we have represented as w dw. Okay. Now since we are doing dot product, okay, so this will be two vectors. This will be my force. This will be my displacement. So this is dot product between these two vectors, force and displacement. And when we use the formula, so you see that f dx cos 180. Why we have written 180? Because we are, the charge q0 he is doing work against the electric field. Right, he's moving in this direction, but my electric field or force, whatever it may be, it is in this direction. Due to this oppositely directed vectors, you are having this angle 180. Okay, but we need to find our total work done. Total work done between when the charge is actually this charge, he's moving from infinity to this point P. Yes, so we need to find our entire work done in moving from infinity to point P. So how we can do that? So we simply integrate it. We integrate our dw value. As you can see here, we are integrating it, and we are providing limits. This is my initial value, lower limit, and this is my final value, upper limit. You are having this minus sign because cos 180 degree, we replace this dw value, which is nothing but f dx. We have replaced that. This cos 180 degree is giving me minus sign, because cos 180 is nothing but minus 1. So because of which you are getting a minus sign. Okay. Okay. So here there will be an infinity. Okay. So you replace your f value, express the side f 1 by 4 pi epsilon naught q naught by x square. You replace that value, and then you have this variable x here. So the other factors, these are all constant. So they come out from my integration part. Yes. So you integrate only this x part. You're integrating x here because your variable is x. Okay, so which is nothing but x to the power minus 2. So once you do the integration, so you receive something minus 1 by x here. Again, here you will be having upper limit r, and you will have lower limit infinity. You can make this correction now. So once you replace this x by r and then x by infinity, you will receive an expression something like this. Okay, this minus sign and this minus sign, it gets cancelled, and you will have a positive quadrant there. Right, now this is the amount of work done by this test charge q0 in moving from infinity to a point P, which is at R distance from source charge, capital Q. All right, this is the total amount of work done. But we have defined electric potential, so it is nothing but work done by unit positive charge in moving from infinity to any point in an electric field, right, against the electric field. So what we do, we divide it by test charge value, as you can see here. So the work done is being divided by the test charge, the value of the charge, and we receive something like this: 1 by 4 pi epsilon naught Q by R. So as you can see here, potential is inversely proportional to my distance. So this is the expression of potential in terms of source charge, okay, plus Q. See, we have two expressions of potential. The first one which we did, that is in terms of test charge. This one, and this expression which we have derived, this is in terms of source charge. Okay. So as you can see here, I clearly mentioned that however the electric potential due to a point charge depends only on the distance, point of observation from the charge, that is V is inversely proportional to R and not on the direction. You see, when we are finding out our potential, we have clearly defined that it is nothing but work done, right? So we know that work done is nothing but a scalar quantity. So electric potential is also a scalar quantity. It has no direction. All we need to know is that at which point you are considering. Based on that point, we will be able to find out our electric potential value, right? The closer our point is, the more stronger the electric potential is going to be. The more far away our point is, the more weaker or the more negligible our electric potential is going to be. All right. If we consider a point which is an infinity, so potential for that particular point, which is at infinity, is taken to be almost zero. Right? Is taken to be zero. You can say that. All right. So this is what our expression tells. All right. Next, we are going to discuss potential difference. So potential difference is nothing but difference of electric potential between 2 points. As you can see here in this diagram, that you are having this plus Q charge, and you are having these 2 points. Let's say B, and this is my point B. Now, since B is closer to this source charge, this is my source charge. All right. Since this is my source charge, so he is generating my electric field. So at this point, if I want to know what is my potential, so this V suffix B is the potential at this point P, and V suffix A is the potential at this point A. Okay. Now let's say that you consider another test charge. So this is my test charge Q0, which is placed at this point A. Now, if this test charge is moving in this direction, let's say from point A to point B, okay, so again, he does some work there. That work, let us say it is nothing but WAB. So this is the amount of work done by this test charge Q0 in moving from point A to point B. So when we are finding out a potential difference, so this is my potential difference del V, which is nothing but difference of potential between B and A. Since point B is much closer to this source charge, so the potential for B is way greater than the potential than A. So we find out the difference between them, and we can find out the difference using this expression, work done by test charge, WAB by Q0, right? So the SI unit of potential difference or electric potential is volt. We know that, these things you have studied in class 10 only. And this is the definition of 1 volt, 1 joule by 1 coulomb. So this is nothing but 1 volt is nothing but work done by a charge of 1 coulomb, and that work done value is 1 joule. So when you replace that 1 joule and when you divide that 1 joule with that 1 coulomb value, so you get nothing but 1 volt. We have studied that in class 10. Okay. So this is the variation of both electric field and potential with respect to R. That means distance. So along this axis, you are having your distance. along this axis, you are having both potential and electric field. That is why you are having two slopes here, two graphs here. Okay, two graphs you are having. This dotted line, dashed line, is the graph for electric field, and this solid line is the graph for electric potential. As electric field is inversely proportional to R square, so you are having this dotted line as the graph. As potential is inversely proportional to R, so this is the graph for your potential. Okay. Now you can make the difference. You see, this electric field is inversely proportional to R square, and potential is inversely proportional to R. So that's why there is a certain difference in power. So if you can remember that who is of larger value, right? So the more lesser this electric field is going to be, and here again, the larger the R value, the more lesser the potential is going to be. So this is how the variation comes across. Okay. All right. Thank you.